Okay, it's good. Okay, let's press our head. Okay, so ni kita nak masuk yang real punya transformer. So dia akan sedikit challenge untuk kita, tapi it's very easy to understand. Okay, so the practical transformer actually is it's different from the ideal transformer in several ways, of course. Okay, the first of all, because of the resistance of the winding. So the winding, so inside the winding, they use a copper wire. So dalam copper wire tu dia ada resistance. So resistance tu they call it so ada loss lah. So ada loss juga kat situ. So therefore any calculation, the output will be reduced lah. Okay. And also the flux leakage. So between the winding, so between the winding somewhere here, the flux leakage. Okay, flux leakage. Okay. So this one is leading to the inductive reactance. Okay, inductance reactant effect. So once you can see when you heard the leading to inductive reactance, so the symbol for the flux leakage will be in the term of inductance. Okay. And then the magnetizing current. Okay, magnetizing current is not zero. Okay, but it may be a little as a 3% of the load current. Load current dia daripada output lah. Okay. And then there is a power loss in the iron core. So iron core also ada power loss is due to the hysteresis and also the eddy current. Okay, and then a capacitive effect present in the high voltage transformer, affecting the ability to withstand the strike of lighting. Okay, sometimes however okay, from this point upward, the capacitive effect will be not covered. Okay, so imagine the real transformer. So this is the supply power, so the primary voltage. So when we apply current, okay, so the current will induce the flux, so magnetic flux. So and then we know that in between the winding here there will be a leakage. So the leakage is called as a flux leakage primary. Okay, okay. So they will induce, so the others, so yang mana yang tak leakage, so they will go through here. Okay, okay. So same goes to the secondary. So they also induce. So when there is a flux, they will induce current. So the current will induce magnetic flux. So the magnetic flux also will go to here. So you can see from here this one. Okay. Plus this one, so they call it as a mutual flux. Okay, mutual flux. Okay, so this is the secondary flux leakage and this is the mutual. Okay, the induced flux from the primary and also the secondary side, so become mutual flux. Okay, so this is a mutual flux. And this is the leakage flux for the secondary and also the primary side. Okay, so the average, they call it as average. Average the flux at the primary side, okay, will be the mutual flux plus the leakage. Okay, same goes to the secondary. Okay, where is the mean average flux? They call it average flux. Okay, average flux is actually the plus minus this together, the mutual flux plus the leakage. Okay. So why they use a average? Actually, it's because of Faraday's law. Okay. So we know that this lambda symbol here actually is a summation of the flux for each line, for each coil. Okay. Okay, previously we can see the Faraday's law is only n d theta over dt. Okay, so and then for the real situation, actually there will be only d theta like this. Okay, so this is the Faraday's law. So this is due to the actually this part they can they assume that the all line, okay, all each winding, each line here will be produce the same flux. Okay, so however, since we have a leakage, so the each line not produce the same. Okay, therefore they use only this symbol lah. They use a lambda. So summation of all. Okay, summation of all produce flux. Okay, so to get an average flux, we just divide the lambda by n. Okay, by the number of turn. Okay, number of turn. How many line ada, so how many turn. Okay, so then they become like this. Okay, so they call it as a average. So from here you can see there is no, they assume all produce the same. However, from this situation they use a average flux. Okay, average flux. Okay, so yeah, there is two things over here. The first is mutual flux, which is the flux which remain in the core and they link both winding. So the leakage flux, as you know before I mentioned. So this is the voltage ratio across the transformer. Mana gambar ni? So yeah, ni kita mana aku punya ni? Okay, so wait, I try to get the highlight. Okay, so from here the VP, okay, the induced it's like an induced voltage. So we try to expand this part. This part we try to expand. So there is a mutual plus the leakage. Okay, same goes to the secondary side. Okay, so mutual plus the leakage. Okay, so this is the EP and this is the ELP, ES and also ELS. Okay, so this side is due to the mutual part, EP and also ES. So in summary, we can write like this: VP equal to EP plus ELP. Okay, so this side also. So now you can imagine, so there is a relation between the primary and also the secondary through the mutual flux. Okay, so we take the mutual flux, the induced voltage in the mutual part. Okay, so we can see that dm over dt will be the same for both. So this side will be the same. So this one we try to tarik bawah sini, and then we try to get the relationship between the primary and secondary. Okay, so they will become EP divided by ET equal to NP equal to NS equal to turn ratio. So from here what you can see, apa yang you boleh nampak dekat sini? Hello, what we can see from this equation, the final one? you can see that it's similar to the ideal lah. Okay, to the ideal transformer. Okay, so lebih kurang dia. Okay, so this is the important part which is the assumption. Assumption. So since a well-designed transformer, so the flux, the mutual flux is very large, okay, compared to the leakage, okay, compared to the primary leakage and also the secondary leakage. So the ratio of the total voltage and the primary transformer to the total voltage of the secondary transformer is approximately become same as ideal transformer. So this part they assume as 0. Okay, so this part they assume as 0. Okay, so therefore they are not using in the equation, so they assume 0. So the smaller the leakage flux of the transformer, the closer the total transformer ratio approximate to the ideal transformer. Okay, so therefore the supply and the induced voltage will be the same. Okay, similar because they assume, because the loss is very small. Okay, yeah, same goes to here. Okay, so this one become A. Okay, turn ratio. So this happen because the current draw by the primary winding I is very small. Okay, so ni kita assume dia kecil dia akan jadi sama juga. Okay, so now the magnetization current in the real transformer. Okay, so the current flow in primary circuit consists of two things, two current. Okay, first is the magnetization current, which is the IM, to produce the flux in the transformer core. So yeah, the current produced due to the magnetization current. Okay, and then the second one is the core loss current. Okay, the core loss current is the hysteresis and also the eddy current. Okay, so the total up of these together become the excitation current. They call it as a excitation current. So the average flux in the core. So this is the equation. So kalau kita tengok from the Faraday's law. So Faraday's law kita boleh tulis balik lah macam ni lah. Ibarat dia macam ni lah. So become NP d flux over dt. Okay, so once bila kita nak tukarkan dia, so from differentiation become integration lah. Okay, so the average flux. Okay, so you can imagine kalau if the flux, if Vp is the cause, okay, so they mention here, if Vp is equal to Vm, Vm is a maximum magnitude. Okay, if Vp is Vm cos omega t, so then we try to integrate. Okay, so they will become average flux will be Vm over omega np multiply with sin omega t. Okay, so this is the average value, average magnitude, and also the phase. Okay, so yeah, by using the diagram will be easier. So we know that in the previous chapter we know that there is a saturation curve. Okay, so when there is a saturation curve, so whatever current you increase, the flux will increase a little bit only. Okay, so look at here. So we have Vp and we have a flux over here. So once the flux increase, okay, bila flux tu increase, kita tengok sebelah ni kita relate kan ni sebelah ni. Okay, kita tengok kawasan ni. So when flux increase until the magnetization curve. Okay, so bila dia increase, dia akan reach the maximum saturation curve lah. Okay, saturation region over here. Okay, so we also in the same time we try to draw the current. Okay, so yeah, because of current induced, okay, and also the current supply. So okay, when they increase for the flux up to the saturation region, so the current maximum will also reach. Okay, so dia akan sinusoidal lah kat sini, sinusoidal kan, gerak atas bawah macam tu. So dia akan go through magnetization current, magnetization curve. Okay, so the IM you can see is not sinusoidal. Dia ada macam curve sikit kat sini. Actually is due to the this part lah. Okay, it's due to this part. Okay, magnetization curve. Okay, so therefore they become like this. Okay, so for more information, please watch these two video. So this is important. So I think this explanation is more clear. Okay, please watch this video. It is very important. Okay, so this one from the magnetization current. Okay, so however from the losses, the losses at the eddy current and hysteresis, it's also a non-linear, and the fundamental component of the core loss current is in phase with the voltage apply. So boleh tengok voltage pula kat belakang ni. Okay, so voltage belakang ni dia akan follow, so current tu akan follow voltage. So eddy current and also hysteresis ni dia akan follow voltage. Okay, dia akan follow voltage. Okay, so we have the IM. Kita tengok ni current tadi, dia macam ni kan. So this is the IH plus E. We also have the macam mana tadi, like this kan, something like this, the IM. So plus this together. Okay, so plus this together, I excitation IM plus I H plus E, so will be like this graph. Okay, will be like this graph. Okay, the dot is a voltage. So this is the summation, the total excitation current. Why this happen is actually is because of the harmonic equation, harmonic effect. So harmonic effect tu dia ada sinusoidal banyak, satu frekuensi tinggi, satu frekuensi rendah, so dia akan ada effect. So bila dia combine together, so they will become like this graph. Okay, but it's okay. From that video you can understand more. Okay, so this is the dot conversion. I think I explained before, so I can skip. Okay, so the net MMF, the magnetic force for the both side. So yeah, for the ideal actually, when we plus together, when we minus the NP multiplied with IP minus NS and IS, they will become 0 for the ideal. Okay, for the real transformer, it's not ideal, but it assumes the value of R, the reluctance is very small. Okay, so since R is very small, so we assume the value is they become 0. Okay, so nearly 0 as long as the core is unsaturated. So therefore they become like this. So the explanation for the real transformer and also the ideal transformer a little bit different, but end up the equation used is the same. Okay, so then we know lah already the real transformer punya conversion, the current, the turn ratio is actually the same equation between ideal and the real one. Okay, so in order to generate the magnetization current, the equivalent circuit, okay, in order to generate the equivalent circuit, we need to know the loss, okay, because to generate the equivalent circuit, actually it depends on the loss. Okay, so there is a 4 types of losses. Okay, the first one is the copper. Okay, the copper losses, which is the I square R. Actually, as resistive heating losses in the primary and secondary winding. Okay, resistive heating, primary winding. Please be reminded, copper losses actually is in the winding, the wire itself. Okay, in the wire. Okay, and then eddy current, resistive heating losses in the core. Okay, ini core. So eddy current kat sini, hysteresis kat sini. Okay, so same goes to the hysteresis associated with the rearrangement of the magnetic domain. So yang I think saya dah tanya sebelum ni. And then the leakage flux. Okay, leakage flux for the primary and the secondary. Okay, so please watch the video also. So the equivalent circuit, bila dia transform, dia akan jadi, kita tadi ada core kan. So bila copper losses, dia kata resistive. So ini become macam resistor lah. So eddy current resistive in the core. So ni also become resistor. Okay. Leakage, ni they will assume as a inductant. Okay. So ni combine together lah. Oh, dia ada lagi satu lagi, magnetization current tu. Okay. So ini transformer punya construction. So ada transformer simbol dan sebagainya. So ini tadi. Okay, so dia akan jadi sebeginilah. Okay, so this is a copper. So dia akan jadi macam ni, ada resistor, ada inductance, and then they divide by 2. So one is the magnetization current. Okay, this is the magnetization current, and this is the eddy current ataupun hysteresis losses. Okay, and this is the yang ELP tadi tu. Okay, losses. Okay, this is the winding ataupun copper losses. Copper losses. Okay, so nanti saya katakan satu-satu. Ini antara dia punya explanation video. Okay, so saya highlightkan satu-satu yang di sini. So boleh tengok kat sini. So this inductance, okay, for the primary side and also the secondary side, actually is based on the leakage flux. Okay, leakage flux. So which is this one is flux LP, and this is flux S. Apa pula ni, PL lah, silap. LP loss, betul. LP ni what? LS. This one is LS. Okay, the resistor here is based on copper losses. So for the primary side and the secondary side. So this part, what is this part? So this part is core loss current, and also this one is the magnetization current. Magnetization component. Actually I can say component. Okay, so this is how we refer. So yeah, how we can refer this side. Okay, so this side, how we can refer to the primary side. Okay, so once we refer to the primary side, they will become like this. Okay, like this equation like this circuit lah. However, this part macam agak terganggu kan, macam kacau sikit kan. So this part macam kacau sikit. So this part boleh macam ditransferkan ke belakang. Okay, so dia boleh transferkan je lah. Okay, so dia move this part to somewhere to this part lah. Okay, dia join tu dia tukarkan. Okay, and then baru boleh buat R equivalent and also E equivalent lah. So dia just plus minus je lah. Tadi dia jadi series lah. Okay, so banyak assumption, banyak perubahan yang dibuat lah dekat circuit ni untuk memudahkan calculation Okay, so at last the part tu dia hilang dah. Okay, at last part tu hilang. Okay, part yang tadi tu dia remove je. Okay, so untuk calculation dan sebagainya, benda tu dia just remove je lah. Okay, dia ignore je benda tu. Okay, so this is the how we transform to the secondary part. Tadi to secondary part, from the secondary to primary. So now from primary to secondary. So this is the equation. Okay. So sama lah, dia punya tu hilang dia remove je. Okay, so tak ada apa-apa penambahan je lah. Okay. So ini example 2. Ada apa-apa soalan tak?
Tak lagi.
Boleh faham tak sekarang ni? Saya yakin ada masalah pemahaman tu mungkin dekat magnetization current tadi tu lah. Saya yakin Tapi jangan risau, bila you tengok video yang saya kirimkan tadi tu, you akan lebih faham lah. You kena explore sikit lah benda tu. Okay, apa pun dia punya calculation dia sebenarnya simple saja, sangat simple. Calculation dia sangat simple. Okay, so step down, kita tengok example step down transformer is rated at 1000 kilo watt ampere. Volt ampere 7200 divided by 277. Okay, and has the following equation parameter. So ni kita ada RP, kita ada RS, semua information kita ada dekat sini lah. Okay, so find the equivalent winding. So kalau kita tengok, kita boleh direct lukis lah. Okay, jangan lupa once dalam soalan ke apa kan, bila kita bagi soalan, kadang-kadang kita suruh lukis dapat markah So you ada lukis resistor, ada ni, and then you ada pecahkan ni, sini macam ni. Okay, and ni, okay, ni pun sama. So ni ada resistor, ni ada inductance. Okay, so you just write ni RS, ini XS, ini XP, ini RP, ni RC ataupun RM, ni RM, ni XM. Okay, so first of all, bila dia write macam ni so this is, kita boleh tahu lah ni primary primary voltage, and also ni secondary voltage Okay, so kat situ kita boleh terus dapat dia punya ratio turn ratio So dia nak R equivalent, so kita transform kan yang secondary ni, kita transform ke secondary pergi ke primary Okay, nak transform RS ni, kita boleh buat kalau nak RS prime is equal to A mana tadi? A square RS Okay, dia buat macam ni lah. So bila dia dah tambah ni, dia akan jadi in series So ini bahagian ni kita boleh ignore dulu. Okay, so kita transformkan resistor, and then kita transformkan inductance. Ini dia transformkan satu-satu lah. Kalau kita tengok example 1, dia gunakan Z tu kan, ZS tu. So ini kita RS, plus dengan XS. Okay, ni J. Okay, so dia transform kan terus lah. Okay, so Z equivalent equal to ZP plus ZS prime. Okay, so ini dia buat satu-satu lah kali ni. Dia buat satu-satu, R equivalent, dia tambahkan, dia terus tambah, so dapat Z equivalent. Okay, so equivalent impedance also dia sama lah. Secondary, ini low to secondary side. So ini refer to the primary side. Okay, ni primary side. Okay, ni kalau kita refer kepada primary side. So ini kalau kita refer kepada secondary side, terpindahkan dia ke sebelah kanan pula. Okay, so kita tengok kat sini lah. So tadi kita tengok dia apa, dia guna equation A square over Z kan, XS ni. Okay, so now dia terbalik lah. Okay, dia tak guna macam tu kan, dia sebab dia transferkan kepada secondary side tu. Okay, okay, so I think kita stop kat sini. So later on saya akan bagi you video supaya you boleh penjelasan lebih detail lah tentang benda ni. So saya nak awak cover dalam video tu ambil yang 2.6 saja. Okay, so ambil yang 2.6 saja. So later on kita akan sambung lah. Minggu depan kita akan terus pergi 2.7 Okay, sebab dah ada explanation ni dalam video tersebut. 2.7 ni tak payahlah. So 2.7 ni pun tak masuk dalam syllabus, kita dah keluarkan. Okay, so you cover 2.6 je dalam video tu. Okay, so hari ni punya video pun saya akan transfer. Sekarang kita akan upload lepas ni. Okay, for now ada apa-apa soalan?
No. Not for now.
Okay, so kalau tak ada, kita stop Google Meet ni dekat sini. And kita sambung dalam video. So please watch all the video that I include in the slide. Okay, so yeah, I believe so far the calculation is still the same for the ideal and also the real transformer. Okay, so itu saja untuk Google Meet hari ini. Kita jumpa next week insyaAllah. Okay, Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam. Terima kasih doktor.
Thank you, doktor.